Good morning. I guess there are not many people today. Zake, you prefer to be called Zake or Alexander?
Or Alex.
Alex, okay. Alex is actually a GRA here, and he's actually working on Bayesian networks for traffic prediction. Yeah. So this is one of the papers that he has read, and he's probably going to share with us what the paper or what the research has done. Yeah.
Good morning, everyone. As you know, my name is Alex, and I'm going to present this paper, short-term prediction, border crossing time, and traffic for commercial trucks. A case study on a person which are short. So this is my content. I'll go through the review, the objectives, the method and modifying, and also the results, and conclude. So basically, according to this paper, we identified that short-term prediction has gained so much focus in the past 3 decades, and its main objective is to feed in information into an IT system, that's intelligent transport system. And with such a system, it's able to tell the users the state of the traffic conditions, and also there they can schedule their trips. And this is done by variable message send. The variable message send, that one basically is just that's a message like displayed upon you, and then you can tell from that message that when you read the message saying that okay, Kuala Lumpur route, it's highly congested, then you will know and plan another route to go to this. And this one, since this deals with real time, which is very good, it has been possible with the method that I'm going to show in the next slide. So the author identified these methods, and the category being as parametric. Parametric meaning that it's based on a fixed parametric set. Parametric, the set is not fixed, and hybrid integration is combination of both methods. And these are the methods that are being done for the short-term prediction. And these are the authors that identified. So why this short-term prediction? Why short-term prediction on border crossing? His reason was that most of these papers they focus so much on highways and freeways, but he identified the issue where the little was done to focus on the border crossing. So that's why I say that. Why don't we try and focus on border crossing and find a better way of predicting the traffic conditions? So he identified a few papers, Lin et al. And Wang and Sadek. They came up with actually the original method from Wang and Sadek. They came up with a speeding network algorithm. Basically, that algorithm tries to mimic the function of the brain in such a way as to recall information. Let me say, like, if I've seen something, then I try to recall after some time. And if I recall it correctly, then this speeding network actually tries to also do that kind of function. So Lin et al. Concluded this speeding network algorithm and called it enhanced speeding network. So basically, this enhanced speeding network it developed the SPN and transformed it into a dynamic time mapping algorithm. And according to the author, he said this algorithm, after reading this source, he said that this algorithm is so good for a time series analysis since it provides that optimal pairing of elements of the two time series. So this part, in the border crossing for this section here, it basically focuses on the traffic volume because there are basically two parts. Determining the traffic volume and determining the delay and the border crossing. So this study was based on traffic volume and the border crossing. The next part is basically the delay. So we identified some papers which were focused on the delays, and these are some of the papers have just simulations. The others focused on an area, like him, the Lin et al. The part B, the previous method was part B. So this one was basically trying to predict the delay along that part, the crossing grid. And he identified the first grid, And also there was another case study which this paper actually is focusing on. But for this case, these people were mainly focusing on the delay. They didn't do the prediction part. Basically, this just estimated the delays along that bridge, the massive bridge. So, moving on to the next slide. So this paper was hard to figure out the objective, but from what I read, it's basically his main objective was to, as from the title, determine the volume of traffic on the ambassador bridge, and then also try to determine the time it takes for a truck to cross from one side to another on that same bridge. And of course, with all this, you also have to identify a method which could be possible to perform these functions. So, from the method, I actually use the ANN approach, artificial neural network. Artificial neural network, why I chose this is because it can determine the nonlinear relationship between independent variables and dependent variables. So, without even knowing without having incident knowledge of actually the variables, which makes it good. Compared to other methods, the previous methods that have been focused on short-term, they need all like sample initial data to try and perform that prediction. But for this case, because the AN, because it can easily adapt, it can easily figure out the correlation between the variables, independent and dependent. And then according to this paper, Francis, he also says that this ANN technique, it is so superior, that's why it's able to deal with both categorical and continuous variables. So, from what the author did, he chose a relative neural network to focus and model the traffic volume on that bridge. The ambassador bridge, I'm going to show it in the next slide, just to give a clear picture. So basically, this is the ambassador bridge, connects the USA from, as you can see, from Detroit to Windsor. And these zones that you see actually fulfill the second objective, the crossing time. So the crossing time, basically, it's made up of the time it takes for the truck driver to go from one side to another, as I said before. And then there is also the delay, which is also which is dependent on the carrying delay, and then the inspection time. The inspection time, this is actually truck. Why they chose the truck? Because we wanted to focus on the trade, the US-Canada trade. US-Canada trade is based on the truck transportation. So the inspection time, what he meant here. Okay, now let's imagine there's a truck coming from USA, so it comes here and delays for some time. Zone 1 and 4. These are the zones where they inspect you, they check you, and so there's an additional delay. So as it moves here, of course there will be that queuing delay, there will be all the delays until once it reaches the Canada side, there will also be another additional delay. And all those delays and the crossing time, I mean the time it takes to cross from one side to another, will add up to the crossing time for this part. So according to the paper, he calls this a geophase. The geophase actually is this was described by Transport Canada. Basically, it talks about this is GPS data. The GPS data. This is what helped them figure out the crossing time from the crossing time of this week, and that was due to the pins for each vehicle that gives out a GPS pin. So using those pins, they had to figure out those times, the delays, and yeah. So basically, that's the understanding. As for the method, the multiplier figure neural network, this one, the paper failed to break this one apart. But when I read another paper, of course, according to this source, it was actually hard to get, and you have to buy this download, and so old, you can see, 1996. So to understand this part, let's look at this neuron. A multiplier neural network. Basically, it's made up of three layers. There's the input, there's the hidden layer, and then there's the output. So the main focus is on the hidden layer. So let's consider this neuron here, this neural network. So once you look at this, you notice that its inputs are coming from x1, x2, x3, and x4. Yes. So he didn't specify the inputs. These inputs, according to another journal which I read, imagine it like this. Consider this as a variable, input variables. Yes. Once the variables come in to these nodes and the input, there's actually nothing happening here. You're just putting in, feeding in the network. As I said before, when you look at this node, this is where the magic takes place. So this node accepts the inputs, variables. These are actually independent here and dependent. So they can be both. So x1, x2, x3, x4, the variables, 4 variables are inputted to the H2 neuron. So what the H2 neuron does, it accepts the variable, then it computes its weight. You see, each connection here, the connections here, they reflect the weight of that variable. So it computes that variable by multiplying the variable and the associated weight on this. So after multiplying that variable with this associated weight, it adds up all the products, the variable weight products. And after getting the variable weight products, it will there's a function here associated with the neuron. They call it a transfer function, a computation function. But transfer is better because what it's going to do is going to transfer all these inputs and output them here. And this output will be this actually. This will be the output. So the output of this one represents the summations of all the variables with their respective weights. The product actually. So according to the paper I read from Ghana, the output is the summation of all the weights and the variables together with another. They didn't put it here, but they tried also talk about a bias factor. I think you can tell me that. That bias factor is actually the most important part of this neural network. It makes it so flexible, and with that bias factor, this neural network will try to adapt the situation to the inputs, and then with that adaptability, it will try and also adjust the weights. You know, there are two things here. There's getting the actual output, which will be produced from the neural network, and then the desired output. Let me say, like, I want to send a message. I want to drink water. Okay, I think I can use that example. So the desired amount that I want to drink, maybe it's 500 milliliters, but this one predicts that I'm going to drink for 400 milliliters. So that means there's an error that has been produced. So with that error, there is a technique called back propagation. So with that back propagation, it tries to, its purpose is to try and reduce that error, such that it tries the desired output tries to match with the actual output. And once you achieve that, that means there is no need to do any more more estimation, because it's a process actually. It can go 5 times, 10 times, 11 times, 20, 100, but that process basically tries to minimize the error. I don't know if you can go down to 0, but for this paper, they tried to go close to 0. So that whole technique of trying to adjust the weights to such that the desired output tries to be close to the actual output is what we call training of the network, which is actually the next part that I'm going to talk about. But so basically this paper, feed forward, what I talked about is basically the feed forward. Actually, this means that each layer on this neural network, if the nodes can only connect to other nodes of the subsequent layers, they cannot connect to each other. That's why it is called a feed forward. The other term that they used for the initial networks was called feedback. Feedback is basically where they just connect to each other. But this one, only connections are made to the subsequent layers. This one connects with this one connects with it, but cannot connect to this. So that's why they named it fit for multi-layer because of these layers, and it can also go. You can add more hidden layers, and depending on the inputs to the variables that you put in. Yeah, so that's how I understood it. Yes. Going to the next slide. I've already talked about the propagation. Okay, they used MATLAB, and they just identified some parts. I think that one will take it up. So they say that they use basically this neural network toolbox to model the traffic conditions for both traffic volume and crossing time. That's what I understood from this paper. So when we go to the next part, okay, they explain that MATLAB has 3 algorithms. So they chose the LM. And the reason why they chose that was because the LM was more computer efficient. Yeah. So basically, this was MATLAB and training what I understood. So remember 2 things: modeling traffic conditions of the what? Of the border. They focus on traffic volume and the time it takes per truck pushing one side to another. So according to this paper, they train 2 models to try and model the traffic volume, and then 2 other models to try to try and predict the crossing time, traffic volume and crossing time. 2 models each. So that's what I want to talk about. Okay, so this is the formula. They said the training of a model for the traffic volume depends heavily on this part here. This is called the number of time runs. So the number of time runs, according to the paper, they say this is the most significant factor that determines the traffic volume. As you can see, VT is the traffic volume, and these are the associated times with D being the kind of time runs. And they say that choosing this D was based on the threshold of the correlation quality. So correlation, they say that the correlation between the dependent variable and its significant time runs was the key part to determine that the number of time runs. And according somewhere in the paper, I said that they would have chosen like I think a big number of time lag, but due to some issues, they tried to stick with the results that they trained. So from this diagram, actually, as you can see, they chose the threshold to be 0.5 because according to the graph, the changes actually stopped. There was no like change after this point here. As from the graph, as you can see, it's descending like this. So this pattern here is actually the same, but this part here, the pattern were actually what? They were actually changing, and they said that they did this iteration like over 10 times, and they found out that after this value here, as you can see, the threshold value, from here there is actually no change. There is just the same pattern. Yeah, but here above here it was changing, and as you can see from the color codes, there is US bound and Canada bound. So according to the traffic volume, they determined that the US bound value, the correlation value, was actually 6 based on this graph. That's the US bound. US bound meaning trucks what coming from Canada going to the US. Then the Canada bound, yeah. So as you can see from the graph, the correlation value of the Canada bound, what is the graph is actually this is 8. 6 is here, yeah, and then 8 is this part here. That's why it is above the 0.5. That's what I got from the graph. Yeah. So yeah. So this part actually, this is the drop volume. Then they say there's a part where they say that if you notice for the case of crossing time, there were certain variables that were chosen. based on days, hours, and so they say that the first case they couldn't use those variables because they didn't get any change. They didn't get a high enough accuracy for the track volume. But according to the crossing time for the trucks, they say that these values played a big part in what? In their prediction. So according to the author, they got the what? Very high accuracy. The accuracy increased with those variables, the track volume, the hours of day and days of the week. So the crossing time is actually this equation according to the author. So this is the crossing time, the days, the week, hours of the day, and this is the volume. The volume here. So basically this, as you notice, it is heavily dependent on our day, here, and the volume. But the volume, the truck volume, the number of trucks in the border, they say that those are the hours and the days didn't do much on the accuracy. So, yeah, these are the performance indicators: mean relative percentage error, variance absolute percentage error, and probability percentage error. The MAPE, MAPE, that one determines the error between the desired output and the actual output. Yeah. The variance absolute percentage error determines the stability of the ANN. Yes. And then the PPE, this one deals with the prediction accuracy of the model. So basically that's it. So from here you can see the number of observations N, the Y is the observed value, and there's other Y is the predicted value. So as you can see from these equations, this is actually the basis. This equation here is actually the core of the propagation. Here, where you try to minimize the error percentage. So from here they try to expand and try to figure out the reliability, the accuracy, and the stability of the hand. Okay, so I missed that part. So as you can see from the graphs, this one actually very easy. But you can just notice that for the crossing time, the Canada bound was actually lower than the US bound. And the reason why they gave this was because of the inspection time that I showed you the time. So the inspection, therefore, who deal with the inspection? There were actually few during the daytime, especially on Tuesday and Wednesday. That's why there was a lot of delay for the US bound. But during towards Friday, the inspections are actually increased. So that's why there is generally a lot delay. That's for a week.
This is average per truck.
Yes.
Per truck. Crossing time from zone 1 to zone 4.
Yes.
Very fast.
Yeah.
It's like the bridge is very small.
Yeah. But it should,
So and then the inspection is fast.
So this is in a week. So there is one for the what? There is one for this is in the day. As you can see in the day, they notice that as you go towards morning hours, okay, this is night time. From 10 until I think 10. That's where you get some issues. Yeah. So that's the trade. I think there's a trade and balancing. So they so that the Canada bound. Yeah. So you can see from this, you can tell that the US bound, the delay is significantly higher. As you can see on the graph, there is also one for the year.
Relatively, it's very fast compared to Malaysia.
So this is now a year. Their period actually, according to the paper, they got this data. This was I think 2013. Yeah. So I think it's 2013 data. So as you see, Canada is so consistent. Yeah. But US bound, I think there's so much security. That's why we had delays. And actually, he talked about something else. I think this is because of according to the paper, it's because of the 9/11 attacks. That's why the delays are so high, as in there is so much security checking and everything, so that's why they got too much delay. So it's significant high delay compared to the Canada law. Yeah. So when it comes to the training, they actually all the trainings that they did here, both the crossing training and the first group, they used 80% training. The first group of observations, they used 80% of training. This is the training part. This is the training. They did 3 parts: the training part, validation part, and the testing part. They put so much emphasis here on the training, 80%. They focused on this part. The validation was just for network generalization, and then the testing part was, I think, for accuracy, the prediction. Yeah. So as you can see from here, they only considered the track ruling for the US bond. As you can see from the graphs, it was so high. I think that's why they focused on that. And as you can see, the correlation value, the one that I talked about, it is greater than 0.9. Generally, just over 0.9. Yeah. So when they say this is the, because of this value, the modeling really did well because of this value, the 0.9. So the higher, the better. Yeah. So that's for the track volume for US. They didn't put the Canada. Yeah. So as we go to the next slides, after they talk about the crossing time, traffic volume. So as you can see from here, they got a correction value of 0.93. Oh, by the way, for this part, you understand this part? This part is the desired output. This is the output from the model. Yeah. So this was a very good correlation for the observation. But they say as it went to the validation now, the testing kind of reduced, but still accepted according to the author. So this is for the US bound. So they got generally a value of 0.7 from the testing part, as you can see from here.
Validation is much more higher.
Yeah.
Why is that so?
I don't know. It could be the models that they use. That's what I think. It could be the models or the method that they use. I think the model may play a significant factor in this. So this is for the US bound track. The Canada one, surprisingly, it is higher. But yeah, I think that one you understood from the graph. So this is the training, validation. Actually, the test is actually higher than validation. So that's where I was a bit confused on that. But yeah, so this is the Canada one, and they say this is actually okay, which is better than the US bound.
You say all training, validation, then test is actual data.
Test, how can I put it? According to the author, they say the testing part was actually prediction. As in, that's like the final.
Then all?
They say that they have to do all the observations according to the paper. It was a bit confusing, actually. But they say they did the training, the validation, the test all together. So this one is a bit unclear, but this is what they did.
What's the division between the training and tested?
The training was 80%, and the validation test each was 10%.
10 months.
No, the 10 months was for the, I think, the drop volume. Then the GPS was 3 months.
Oh.
Yeah, but I'm going to show it on the next one. Yeah. So, but it was in the previous one.
Really for them is a linear model.
Yeah. So. So this, according to them, as you can see from here, the model actually predicted the what? Yes, the desired output. So it was so good. I think it was 90%, 95%. As you can see from the graph here. This is, as you can see, the up part. The up part is the US bound, and the bottom part is the Canada bound. Yeah, so Canada, I think because of the lower delays, they have a better compared to the US one, which has so many few delays. So, according to the table here, the map, if you remember, this one determines the error between the desired output and actual output. And for me, I got very low value difference. So, US bound, I would expect the Canada bound to be lower here, but I don't know why they got the US lower. But yeah. So for the APE, this one determines the stability, the APE model, and this is what they got, and they said it was good, so the lower the better. The PPE, this one determines the prediction accuracy. So as you can see from the figures, it was good 90% and 88%. And they went ahead and used they compared with other approaches using the same training methods. It was RMX, multi-layer passive network, and radio basis network. And as you can see from the figures here, it beat all of them. This was the weakest. So compared to these values, it performed the best when compared to other things. So I forgot to mention this part. The part where I said there was some software they used. It was called I think Palisade. Palisade, they used that part determine the impact. I think I put it there. But they use Palisade software to determine the impact of the independent variables on both US. Yeah. So from what they got from this result here, they say this factor, the hours, were the main significant part for determining the processing time compared to days and track volume. When they're figuring out the impact of independent variable, they found out that this hour, according to this graph here, plays the most significant part for determining the processing time on the track performance side. So as you can see, also days plays a bit here, important part, but this one is the king. Yeah, it's the top part compared to the top one, which is.
So the data from the hours is most important.
Yeah. So hours is so important, even from the graph. Because if you go back to the graph, yeah, there are many variations, but to the mark, it is.
But you don't have volume graph, track volume graph.
The volume graph is actually this. The volume graph. I think
This correlation.
I think it was correlation.
Yeah. We need
Okay, this is processing time. They did focus much on the volume because this one is the only part that explains the volume part. They basically focus on processing time. So track volume, because the track volume did not they did not choose the variables which are concerned with time, as in the days, the hours. They did affect this part so much. Yeah, but this one played also. It played just a small portion part to determine the processing time. If you see from this equation here, this one, according to this equation, the track volume also plays a part in the processing time. Yeah, but according to this paper, hours is the major factor that plays the prediction of the processing time. So, yeah, I think this was supposed to be the data set. So, the other TMS, the remote traffic microwave sensors, this is what they use to determine the volume, the track volume. And this is the source of cross-border institute of University. So, the GPS, this one I think I already showed you, the GeoFence, the ambassador grid. This was one that played, that helped in determining the processing time. Yeah. And it was in one year period. I think I'd say 3 months. This one is 1 year. And TMS was 2 months. Yeah. So conclusion, according to them, based on the MAPE, the PPE, it showed that this method is actually, it really proved that the focusing probability of the AN model was so high, and they also suggested that this, if they can use this model for the future ITS technologies for prediction of the short-term traffic, it would be also good. But one issue that of course I think you'll notice, since they use data of the previous past, of the previous history, it was not real time. They just got like a sample, fed it in the AN model, it did its work, and came out with the results. So they suggested that if it was possible to continuously feed real-time data, that would actually improve this work and the method. And they suggested that if you can use auto license plate readers, this can actually cover the real-time portion, the real-time data. Yeah. So that's my presentation.
A few questions. Is your correlation coming from very, very far back, 0.5, that 0.5 thing?
Oh.
Yeah.
This one here. This timeline is in days?
This timeline I'm not so sure about this price. I'm not so sure about this price. But
Yes,
yes,
scale, it's T
It's the
minus
periodicity
1,
of
T
the time
minus
series,
2.
right?
So you can say it's time minus T minus 6. It could be, I think, days or hours or so.
Yeah, so
Yeah.
only one is the.
So it's like it's just like a scale factor.
Yeah,
like that.
what's the period?
the period here. That one I have to get it. But it could be, according to this, it could be.
Because you said in the finance it's short term. So what is short term to them? Short term is hours or short term is days? Definitely not months, I think.
You said it's the difference. So
Yeah.
that means, okay, according
If you
to
go back to the
they put-
equation, if you go back to the equation before that,
Doesn't say.
yes. So it's
Yeah.
T minus 1, T minus 2, T minus T, number of timelines.
Mm.
So that's why the D depends on, is it the data you're feeding in, is it hours data or days data?
Data is
So
So Zake, this particular figure, right? You know what time unit they use it?
Yeah. They according to but they use 15-minute duration.
15 minutes.
Yeah. They said 1 minute was too wasn't good because
15 minutes only 1.5 hours.
Yeah.
they use four
Yes.
minutes now. Yeah, so they use 15 minutes. Yeah, of course that was the favorite. That's favorite then. But 1 minute it couldn't work because of the
The
computation.
result is suggests
Yeah.
time, hour.
So back to that graph again.
They,
This correlation, is this correlation between dependent variables?
it's-
What are the dependent variables?
The dependent variables, I think, according for this case, is the truck volume,
Huh?
the processing time, the time it takes to process the read, and also the delay that they count. So that's what I understood from this. There are three variables that they try to focus on: the truck volume, the delay in processing the read, and the total time.
Oh, those variables. Okay.
Yeah. So
So the input to the neural network is not this variable, right? The input to the neural network is the one you have at the end, the day of week, month, day of week, and truck volume.
yes.
But what's the fourth variable? Do you know? Because your input has 4 variables, right?
The fourth one,
Is it the bias?
the bias they consider this.
It's one.
That's why I say this paper didn't try to explain that part. But the bias, from what I got, it's actually the error that you get from against the user of this. Yeah. And that's what determines actually the adjustment of the actual input and the input. They try to adjust and try to match.
So in this work, they are investigating the factors, dependent variable in isolation. Is that right? They're just checking by. It's not multivariate. You're not looking at. You're looking at 4 fact. You have a plot of 4 more factors.
Factors.
Keep going to the result part.
What?
So go on. All right. That's
Again.
go on. Go on. Go on. Again.
That's the. Okay, that's
Your independent variables are volume, days, and hours.
yeah. That's for determining the processing time. That's the processing time.
And those are the values you feed into your neural network.
Yes. According to them, yeah. These are the values, and they found out that this hour played a more significant part in the processing time because they're independent of it. So.
So volume, number of days, the day of the week, the hour of the processing. These are your three inputs.
Yeah.
Or rather, three input of this work. And they treat the truck the same.
They treat the
18-wheeler versus 1-ton truck versus your garbage truck is all treated the same.
yeah, according to this paper. But I think I forgot to mention some part. I think I didn't put it in the conclusion. But they said that also if you can use also portions of the truck, that can also try to improve, I think, the prediction. But because they just considered just one truck, and actually the trucks were based on GPS pin, as I told you, the GPS data. So the GPS data that they used in each pin was representing what I think like the time how can I call it? I think the time stances for crossing one bit to another. Because if you look at this there, if you look at this, the grid, so they say that this geofence was actually providing pins. And
this is based on GPS, isn't it?
yeah. So the geofence which are described by Canada, they say that it works in such a way that each truck emits a pin. So that pin it has a timestamp and I think an anonymous identifier. So with those pins, they were able to determine that crossing time, but they couldn't tell whether it was a garbage truck, let's say a fuel truck or something. So I think it was a general case.
What is the motivation of reading and presenting this paper? Is it in line with your research?
It's yeah.
So what you are doing for research in
My-
summary?
Since I'm an student,
Yeah.
so my type of local and context sensitive traffic predictive condition
Okay.
analytics by since I've started on the traffic prediction. So that I'm still at the ministerial.
I
So
see.
I think I've covered the traffic prediction.
It's actually very closely what he's doing, except that he's trying to predict traffic, but we haven't decided what
Yes,
whether it's
it's a
time or whether it's jam or not jam. And but the intention is to use dynamic Bayesian networks.
Okay.
So maybe you can compare this
Bayesian networks is the Markov models lah.
dynamic feedback, Bayesian feedback actually. Is this data available?
That I need to confirm. But if it is, it will explain. It will really describe.
Because if this data is available, then it makes your own work a little bit easier to compare. Yeah, you can use the data.
If it is private, that means it will be.
You can ask them, because it's quite new papers.
Yeah,
2014, right?
Actually, this is 2016.
2016.
Yeah, they accepted the paper last last December, Tuesday, and they
Yes.
did all the
And you can have, you can do some, ask them for the data or whatnot, and apply using Bayesian or something, just to try it out. And maybe you get an idea of whether it's going to work or not.
Generally, develop a knowledge of how they use CNNC. How do you plan to apply knowledge share into your work? Any idea?
The knowledge sharing to my work this.
Yeah, how can you apply this? Do you plan to apply any of the algorithms and methods?
Actually, I not yet decided because I wanted just finish engineering. So when Dr. Puto told me to pick out a paper, I just randomly chose this. I thought this was actually the easiest, but I'm yet to decide. Yeah, so right now I'm still.
It's unsupervised, isn't it?
Huh?
Based on networks. It's unsupervised learning network. Is it supervised? Forgotten. Forgotten already. Okay, never mind.
So I'm yet to decide. Yeah. So I just chose this paper, thinking that it would be easy to explain, but the hardest part was this one, actually. They tried to explain this part. So if you know the concept of this, the input, the weights, the adjustment through back propagation.
Yeah.
So yeah, that's my
Okay.
yeah. Any questions?
Alright.
I like your attention to that thing because it's something to you think a bit further.
Zake, can you move closer to the light? Just for just for illumination purposes. Otherwise, you can't. My camera is pretty crappy, so I can't pick you up.
Software you
Okay, there we go.
Except it doesn't come with Windows 10. You have to install separately.
Okay, it came up very well, I guess.
Okay.
Thank you.
Thank you,
very much,
guys.
Alex.
Okay.
Thank you.
Alex.
Well done.
I think it's a good start for you.
Yeah.
Because
Are you using
you're
this?
still recording, or stop already?
Yes, didn't you?